developments. In September 1965, TEG's Orion 1 and Orion 2, based on 210 PO, were launched into a near-Earth orbit as components of the Cosmos 84 and Cosmos 90 satellites. The choice of 210 PO with a specific thermal power of 141 watts and half-life of 138 days allowed for a compact design which incorporated silicon semiconductor converters with an electrical output of 20 watts. The service life was determined mainly by the half-life of 210 PO, and this could reach 3,000 hours. In the mid-1970s, research and development on a complex radionuclide radioisotope power system using 238 Pu was initiated to support long-term research of Mars. This power system, named VISIT, included an RTG with an electrical power output of about of scale models as well as thermal and electrical prototypes. During this era, key problems connected with the creation of radioisotope power TEGs or RTGs for space were solved, namely the production and processing of the 238 Pu, the production of the cermet tablet fuel based on plutonium dioxide, the structural materials for the manufacture of the RHU capsules with radionuclide, as well as their capability with the fuel composition over a wide temperature range. The RHU single element design a thermoelectric mock-up using an electric heater instead of the radionuclide, with an electrical output of 3.75 watts at the end of life. At end of life was fabricated and tested. Its thermal power was 100 watts. The tellurium, lead, and germanium-based alloy semiconductors in the thermoelectric battery were medium temperature, ones with heat removed by thermal radiation from a ribbed casing. This RTG was proposed for use as a lander power source under ESA's LIDA lunar program. In the late 1990s, RTGs were used as the electrical power supply for the research probes to be landed on Mars as part of the Mars 96 international mission. The mission included long-life small autonomous stations and probes. RTG, RTGs were needed to maintain equipment at design temperatures, to power equipment, and to recharge a battery for communication with the orbiting spacecraft. Thus, 8.5 watt, 238 pu RHUs, and a 200 milliwatt RTG named Angel were developed for the Small Autonomous Station spacecraft. The Angel and RHU are unified products designed to be used both as self-contained units for equipment heating and as the initial heat source to provide the steady heat flow to a thermoelectric converter. The small autonomous station included two RHUs and two RTGs. The complex monoblock radionuclide power system had an electrical power output of about 400 milliwatts and includes a storage battery. 400 watts and includes a storage battery, two RHUs with a thermal power of 8.5 watts each, and a thermoelectric converter. It was developed for the probes. The Angel's cylindrical heat unit D equals 4 cm and H equals C equals 6 cm includes a heat shield case and carbon heat insulation surrounding the radioisotopes ampoule. The ampoule contains about 17 grams of 238 Pu dioxide with an activity of 260 Ci. The ampoule has a dual structure: high corrosion resistant platinum rhodium alloys are used for the inner ampoule casing that contains two ceramic tablets of 238 Pu dioxide clad in iridium. The inner ampoule is hermetically welded and has a release mechanism for dealing with radiogenic helium resulting from the alpha decay of 238 Pu. The low-bearing outer cladding is fabricated from high-strength tan- tantalum tungsten alloys. After hermetically welding, its surface is coated with multi-layer refractory materials. Thus, the radionuclide heat source construction has a double containment in each capsule, and the ampoule itself is additionally protected against outer thermal and impact attacks by heat-resistant carbon material. The Angel radioisotope power TEG or RTG was developed on the same basis: semiconductor thermoelectric materials based on bismuth, bismuth telluride alloys are used as a converter. The RTG generates an electrical power of about 200 watts at an operating voltage of 15 volts at room temperature. The power for the small autonomous station equipment is supplied from the RTG through a nickel cadmium buffer battery. Radioisotope powered TEGs or RTGs of milliwatt electrical power for the space application, such as the Angel RTG and its modifications, are compact, reliable in operation, and have low mass and size, which makes them convenient for probes. The RTG waste heat is enough to maintain design temperatures for equipment working in deep space environments. Further, the RHU is also used for heating gas to warm the instrument module of the Lunoc Hod 1 and Lunoc Hod 2 stations. The heat source's thermal power is 900 watts. Research and development work on thermionic converters, together with the 238 Pu based radionuclide heat sources, is ongoing, with an emphasis being placed on improving energy conversion efficiencies from 8 to 10% to 10 to 14%. Such generators using a thermionic converter with an electrical power of 75 to 150 watts were proposed as the electrical power sources for a rover vehicle under the LEADER program. Thank you, and I will see you on the next one.